Hey, this is Don from Padlock Technologies again with another Superlab. Now, this is going to be a route and switch lab. Now, I did not create this lab per se. There's another person, Rob Riker, by the way, that watched the videos and stuff like that. Now, all I did was just mimic the design per se, but I did routing completely different than what he did for his video. He was actually doing it for a lab. I just did this because, this is how I keep my skills up and up to date. So I did a bunch of routing stuff just to pass the time. So let me go over this a little bit. So this is going to be a OSPF multi-area design. And then it's going to have over here, we have some MPLS L3 VPN going here. We have normal BGP here, different AS, and then we have two ASs that I did not configure yet. Ultimately, what's going to happen is I'm either going to do Flex VPN off of these spokes here or DMVPN phase 3. And I may do OSPF over the top of this or BGP. Since I'm already doing BGP here, I may do BGP over the top, but it really depends. Or I might just do OSPF. And again, if you use OSPF for DMVPN, and you're not using phase 3, now you have to worry about, DR, BDR elections. You have to make sure your spokes are priority zeros so they don't get involved in the DR, BDR election. And if you're not using NHRP, which is the next hop resolution protocol, you have to do broadcast so that the network LSA and the next hop actually flushes out. But if you're going to, or gets mapped, but if you're going to use NHRP, you don't really need to do that anymore. And you can just do point to multi-point design, but that's a whole design question. And I'll get into that if you want to have a video about that. Then here at the bottom, we will be doing BGP, MPBGP, EVPN multi-site. I already have it running over here. I have one data center here, another DC here, and then through my WAN block, I'll be able to get to each of these data centers. So say this is like a colo, so colo here, colo data center here, and then another colo data center here. And that's like I did in my last video, you will be able to see the stretch VLAN 70 and 80 in all three data centers. And then all of these will technically should be able to talk to each other. But again, because of the virtualization of the, this lab, that won't work, but we'll be able to see at least the MAC addresses from each data center for each node that's hooked in. So technically they would be able to talk to each other if this was a real design. I do have I don't have inter AS L3 VPNs. I haven't done a video about that yet, but when I do, I'll give you a little backstory here. Inter AS L3 VPNs are basically four styles here. So there is option A, B, C, and D. Not that many people know about option D. I'm really surprised about that. And that is a combination of A and B, and it's called interhybrid AS. Not a lot of people know about that, but because they really teach just A, B, and C. But look up interhybrid AS. Pretty cool. It takes the control plane of option B and the security of separate VRFs in A. But I will do a lab about that and we'll get more into that. Now I have my internet layer up here. I have not configured the internet yet. When I'm done, internet obviously will come here. It will go through all these AS and I'll be able to ping the internet from everywhere. But let's talk about why, from a design perspective, before I get into the configurations of this, why am I doing multi-area OSPF? And this is for anybody that's about to take the CCIE or anything like this. And I will preface this, there's a lot of stuff in here that I would tell you not to do if you're going to take the CCIE because it's very advanced, high level. But pro tip, don't change anything. If you're going for your CCIE, IE, or EI, sorry, enterprise, don't change anything in the lab. I failed my first one because I decided to get best practice and change a bunch of stuff. Straight failed it. So don't do that, right? It's a technology test. It's not a best practice test. That's the best answer I can give you. If you go in there thinking it's a best practice test, you will fail. But why am I doing multi-area? So multi-area, I'm doing that because I don't want, and I go into, this actually goes into real world example stuff. I go into multiple networks and I see people do a big area zero all over the place. Well, guess what happens when SPF needs to run again. You can have a huge problem with, link state updates and stuff like that, LSA flooding and all that, if something should happen because everything's area 0. Now, there's a caveat to that. Unless you're running incremental SPF, um, you're going to run into a problem. What's incremental SPF is basically I'm going to run, if something happens, a change or anything like that, incremental SPF will run the SPF algorithm on the broken piece or the damaged piece, so to speak, and not the entire uh, network. But most people don't run incremental SPF. And if you don't know, there's a bunch of SPF algorithms. There's normal SPF, incremental SPF, constraint SPF, reverse SPF. We'll get into all that later. If you want a video about the versions of SPF that's run on link state protocols, put it in a comment. I'll make a video about that. But anyway, so we're going to have multi-area here. Now, from a design perspective, we have our internet block, we have our WAN edge block. Remember, I believe I talked about this in a network design conversation, whereas, hey, unless you have a particular reason to combine these two functions, it's really good to split them out, because if you do have to make a change on your internet block, it doesn't affect your WAN block. Unless they're going to the same ISP, then you got a different problem. But I usually do this type of design because, or if I was going to build a network, I would do this type of design because the modular design also allows me to peel off certain pieces of the network without affecting everything else. Now, obviously, going to the internet, if you stop the entire internet, nobody gets out to the internet. WAN block, same thing, right? But if you notice, these are area types are NSSA. Did I say that right? Yeah. NSSA, which is not so stubby area. Now, why am I doing not so stubby areas at my internet block and my WAN block? Well, it's very simple. I want to redistribute routes into my OSPF multi-area, but I don't need I don't need to accept a default route into that area. And if you don't know anything about not so stubby areas, they're going to have 1, 2s, 3s, and 7s. So 3s are allowed to come in, no 4s, no 5s, and 7s are going to be generated when I redistribute from NSSA into a normal area, and those will get translated to type 5s, which are externals. Now they're going to be normally E2s, unless I change the metrics to E1. And if you know, the path selection is intra, inter, E1, E2, N1, N2s. That's how OSPF, think of it like, BGP best path selection. Well, OSPF has the same way, and I just mentioned that, right? So now if I had two exterior, if I had 2 points to go out of, I can actually dictate who's going to translate the 7 into a 5. That's more advanced stuff. And the difference between a type 5 and a type 7 is the forwarding address. The forwarding address is kind of kept in the 7, and then routing will dictate, hey, if there's multiple paths to get there, that's why you have the forwarding address. Usually in type 5s, the forwarding address is just quad zeros, and that just means go to your ABR for that. So I'm going to redistribute at least the 0 down here. Now, here's the thing about redistribution of 0. That's not going to work, right? You have to just do default information originate. Now, in NSSAs, you have to do it in the NSSA area. If you just do default information originate, it will not propagate a quad 0 into your network. So you have to do area, whatever your area is, default information originate. I would not do always. You want to kind of dictate it based on if there's a quad 0 in your routing table. Since it's a static address, it's always going to be there. But if you were doing BGP to the edge, well, if the internet went down, quad zeros would, not be there, because you're probably going to get a quad 0 from your ISP, removes it out of the routing table, which now removes the default originate or the quad 0 from being advertised into your OSPF network. Same thing on the WAN edge side, which is basically running BGP right now to these two service providers, because I did not configure these two up top. Now, the only difference is this is MPLS L3 VPN, and this little thing that I built here is it's going to be it's pretty advanced. Some service provider technology in here as well, some service provider techniques as well. So anybody who wants to, when I start getting into this, or when I do a video on this section, you're going to see something not so standard with what you learn in the CCIE EI courses, you're going to see some service provider stuff in here as well. This is normal BGP, so everything is going to be in a global routing table compared to my MPLS L3 VPN, which is going to be in the VRF table. It will not be in global, and then all the routes will be in the VPN v4 table because I'm doing IPv4. If I was doing VPN v6, it would be IPv6. What's the difference between the two? Well, you have a 96. I think I always say bits and bytes. I say that. Well, if you think about the how much is a VPN v4 route, 96, because the RD is 64 plus 32 for the IPv4 address. So you got 96. And obviously for a VPN v6 route, it's going to be 192. That's 128 for the IPv6 address and then 64 for the RD. So and now you're gonna see I'm not doing IPv6, so you don't have to worry about that. Now there's two ways to do IPv6. There's 6PE and 6VPE, but I didn't do any of those in this one. Let's see here. I haven't done anything here. This will be eventually built out. And this right here is a small MPBGP EVPN VXLAN fabric here. I technically can get all the way out to all of these. So if I were to, let's go to this one here. We'll just open this up real quick. So if you want to show IP interface brief, I can't do that in user exec mode. Interface brief. So I am 70.1. If I wanted to get to this server up here, which is 30.10, I could just ping 192.168.30.10. As you can see, I can get there. So I'm going outside of this fabric to the core to now up here in area 400. This is actually back-to-back VPC. So these are all Nexus switches. The two up top here, which is Nexus OS 3 and 4, those are going to be doing HSRP, and then we're going to do back-to-back VPC down to these Nexus switches, which is, I think this is VPC domain 2 and this is VPC domain 1. And then obviously we're going down to each switch there. Now, why would you do back-to-back VPC? I mean, if you were anybody that used to deal with FEXs, it's kind of similar to that, where you would kind of run your, 500, or not 500, your 5K. I don't even want to say 500. Your 5K would be, you know, top of rack switches, if you want to say that. And then your Nexus switches, these could be 9Ks or something like that. Or 7Ks, used to be 7Ks, but are 9Ks. And these will be your master switch. And then the individual switches in the VPC domain would be like your access layer here. Not that many people do that, but it's a design that you could do exactly. But I rarely see this, but it's a design you can do. Again, people, if you're used to like FEXs, just think of it like that. And boy, were the FEX models were that was something else. FEXs with 7Ks. Anybody that knows. And then we have normal VPC down here, which is my campus network, and another. Just say this is another building. I believe. Let me show IP here. I don't know what this. Okay, this is 50 and 60. So again, if I wanted to ping 192.168.30.10, which was in the back-to-back VPC, as you can see, it's working. All right. So all this routing is done. Everything is going to the core. This is a true core design. So this is technically core distribution access layer. This is a traditional 3-tier design here. For my campus layer going up to the core. Now, why would you do that, by the way? Well, the reason why you would do a traditional 3-tier design and why the core should be L3 always, in my opinion, is because the purpose of the core, now, barring that you got the money to do this, by the way, too, because there is a collapse core design, but there is a problem with collapse core, or a con that you got to be worried about. So in a true 3-tier design, the core is L3 because the job of the core is to get packets from one end to the other end as fast as possible. You really shouldn't be doing span and tree in your core, right? Now, if you have a collapsed core design, you might end up with spanning tree because your core and distribution is together. Well, then your access switch connects to your core and distribution. Well, guess what you just did? You just extended your spanning tree instances all the way up to your collapsed core design. So what can happen with that? Well, if you have a layer two loop somewhere, you can, fry your network because that layer two loop is now transited all the way up to the core because there's spanning tree there. And now you have a bunch of problems with a traditional three-tier design. At most, and especially if you're doing this design, which is multi-area, at the most, if I did have a spanning tree problem, say at the campus layer, well, it's only going to go up to the campus layer distribution switch and stop. It's not going to go to the core because this is L3 spanning tree stops here. This is the demarcation point between, layer two and layer three, right? Plus, if something was to happen in this area from an OSPF perspective, it's not going to translate into the other areas. Now, the only thing you're going to get here is maybe loss of reachability information because the LSA type 3 will no longer be generated if for some reason something happens. And if we really want to talk about LSAs, again, threes, OSPF is link state or acts like link state because it has topology information and reachability information, right? The topology information is within area though. And then when you go outside the area, it's just reachability information. So it kind of acts like a distant vector once it leaves its area. But once it's within the area, it knows everything about its area. If you know about distant vector protocols, they're routing by rumor, or you only know about the routes your neighbor tells you about compared to OSPF or ISIS, which is link state, and you know everything within your area. But when you go outside your area, you only got reachability information. So the one thing I did want to tell you guys about here is in VXLAN, I didn't redistribute the connected routes. Why? Well, it's very simple. I have an NSSA. And because NSSAs can't take type 5 routes, if I were to redistribute those in the OSPF, yeah, it would stop at, ISR 6 and NXOX device, but it wouldn't go into the NSSA areas because NSSAs can't take type 5s. So I had to just normally advertise these into OSPF, which makes them a type 3 because it's multi-area. This is 7, I believe this is area 700. This is area 1. Everything has to be connected to area 0 if you're going to do a multi-tier design, unless you're going to do something like virtual links, and that is a band-aid, and it's not something you're supposed to be doing, right? So you can do a virtual link, but don't do that as a solution, ultimate solution. So now that I advertise them as, regular type 3s going in here are from these ABRs, they're type 3s. And then now my NSSA area knows how to get there. For instance, remember, we're going to ASA here, and I'm running OSPF on this as well. So if we go in this NSSA area, and this is active standby, I did not do clustering on this one. If I do show route OSPF, you see here at the bottom, they are seen as inter-area routes. Now, if I were to redistribute those routes, they would be seen as type 5s. And since NSSAs can't take type 5s, these would disappear and I would not be able to get out to the internet. Now, I do have a SVI over here. So if I did wanted to ping, this is going past the firewall here. So if I wanted to ping 200, I think it's 101.254, which is on past the firewall, I can get past the firewall now, all right, which is an SVI on this R67. Only way I'm able to do that is because the ASA knows about how to get back to here, all right? So this was kind of a brief overview of, multi-area OSPF design. There's a bunch of technologies in here. There's a bunch of different area types in here. Why you would do this. Now I'm going to get more into each area with additional videos because I'm doing, I'm still doing HSRP here, but I'm also doing root primary for VLAN 10, I believe is as switch 18. VLAN 20 is switch 17. So we're going to look at from a spanning tree perspective. When you do that type of stuff, we'll look at, I'm running rapid PST plus not MST, because I only got 2 VLANs. You don't need to run MST for that. But we'll see from a port standpoint, what's a root port, what's a designated port, what's an alternative port, which should be blocked, stuff like that. So we'll see a bunch of stuff there. What else will we see? This is normal VPC stuff. And then once we get over to, I think I'm going to do the MPLS L3 VPN. Once we get into that, you're going to see things like MPLS OAM, which is a maintenance thing for MPLS that looks at the data plane and control plane for MPLS to make sure those are working. You'll see prefix suppression, which is limiting your RIB, and which is routing information base, and the lib or LFIB, which is the label forwarding information base. So you will not see labels for a couple of things here. I've also did something called removing propagation of TTL for things that are going through the fabric or through the network, but I can do trace route from one of these PEs. So trace routes from the PE to PE will work, but trace routes coming through the MPLS network will not work because I am not propagating the TTL value, which, if you know how TTL works or trace route works in MPLS, briefly, I'll say this before I end this video. So TTL has, not TTL, a trace route, when you go through MPLS, will have a TTL value of 1. Right? When that 1 gets deprecated, it turns into a ICMP packet in the top labels. So the TTL values will turn into 255, but it'll be an ICMP packet. You might get a label 1, which is a router alert label, and then it looks down and say, oh, I need to change that. So it starts as a UDP packet, and it starts as your trace route, but eventually it turns into an ICMP packet. Now, when you don't propagate the TTL value, what happens is that never happens. That look in the packet and change it to, that never happens. So it never changes the TTL value in your trace route. So you'll never see it actually deprecate. But you need to know how trace route works before we get into that advanced kind of stuff. But I'll show it in the example. So this is Don from Padlock Technologies. I know I talked a lot about this lab. If there's any questions about things you want to see from a routing perspective, put it in the comments and I will do a video like breaking down a lot of these configurations and commands so that they make more sense. Again, I know this looks daunting and it looks like a lot, but once you kind of get the concept, OSPF, like once you know how to read the OSPF database or the ISIS database, which totally different because you got PDUs versus LSAs, stuff like that. Then you have to worry about the pseudo node. But once we get into all that, there's not going to be a pseudo node here because I'm doing network type point to point. So there's no BDR, DR, or DR, BDR election in any of this. But yeah, if you got any comments or questions about any of this stuff, back-to-back VPC, put it in the comments below. Hopefully this overview was informative. Thank you and have a nice day.